Hello everyone, and welcome to the second day of Cloud Native Geospatial event. My name is Sanket Verma, and I'm from all the way from New Delhi, India. Uh, I basically work as a community manager for ZAR. So I am sure you all must have been hearing about ZAR, COG, and all the other formats uh, in the past day. I would be so I do have like a talk and a tutorial later in the day, but this time I will be moderating a couple of lightning talk sessions, and it's so great to see everyone and all of you. So yeah, we got a couple of speakers in our list. So the first talk is by Bjorn Hartel, FlatGeobuf, straight from the horse's mouth. So that seems like a interesting name to me. So Beyond Hartel's talk is basically a recorded presentation. So you would be seeing that on your screen just now.
Hi, and welcome to a lightning talk about FlatGeobuf. My name is Björn, and I'm a Swedish programmer and have been into spatial stuff for a long time. A few years ago, I created FlatGeobuf. So, what is FlatGeobuf? It is a fast binary format for spatial data and attributes. It's lossless and with similar flexibility as GeoJSON. Initially, my idea was to make a format similar to the shapefile, but faster and without the limitations.
You can start the video.
So, why did I make FlatGeobuf?
You can start the recorded video now.
I think it was initially due to that I wanted to know how Mapbox vector tiles work. As you might know, they're based on something called Protobuf, which is from Google. I like to think about that thing as a kind of XML, but for binary. I was also triggered by that the best format out there for some use cases was still the shapefile. Then I found a project called FlatBuffers, which is also from Google, and it's like Protobuf but faster. I also found FlatBush, a tiny and nice implementation of the R3 spatial index by Vladimir Agafonkin, who you might know as the creator of Leaflet. So FlatBush helped me understand how R3s work, which is something I had wanted to learn about for some time. And to create a format to beat the shapefile, you really need an efficient spatial index to support making spatial filtered queries against the data. So around September 2018, I made the initial commits to implement what became FlatGeobuf. It went through several iterations, also at the spec level, and finally in January 2020, I was happy enough with it to consider it more or less done. I implemented support in GDAL, and it was released in GDAL 3.1 in May 2020. That was an important stepping stone for FlatGeobuf to make it available, for example, in QGIS. FlatGeobuf is also available as a plugin in GeoServer, so you can use it as a data source or as a WFS output format. So I haven't mentioned Cloud Native. Well, that is because I didn't consider Cloud Native when I made FlatGeobuf, but it turns out it's pretty much Cloud Native, perhaps by accident. A design goal of the final spec was to make the format I/O efficient. That was to support streaming and piping, and that also makes it works well in Cloud Native. Okay, so a quick demonstration of an example that is also on the FlatGeobuf webpage. And so what happens here when I pan-rate the map is that the browser makes range requests just for the data within the bounding box. Okay, so to sum up the use cases that I have in mind for FlatGeobuf is to use it as a drop-in replacement for the shapefile, JSON, or GML. But you could also use it as a system-to-system communication protocol, or as an output format for WFS or OGC API.
Yeah. Hello. So seems like the video played well, and if there are any questions for Bjorn, he is in the he can see the questions in the chat, questions chat. So I don't really see any questions over here. So yeah, we can take that over to the Gitter. So we have our next speaker with us, Brandon Liu. Hello, Brandon. Uh, I can't hear you.
Hello?
Yeah. Yeah.
Okay, it's working now. Sound good?
Yeah. Hello. How
Awesome.
are you?
Doing well.
Yeah. So Brandon is from Protomaps LLC, and he would be talking about no two clouds are alike. So take it away, Brandon.
Are you able to see my screen share?
Yes, I can.
Okay, awesome. Hey everyone, I'm Brandon. I'm going to be talking about cloud storage today. For context, I'm working on a system called Protomaps. It's an end-to-end system for both packaging and styling maps using only static files. That includes geodata, that includes tile formats, that includes rendering. And it is cloud native from the ground up. It has a tile format called PM tiles that's being developed alongside it. And it's made of mostly open source components that are on GitHub. This is also in the context of a new product I'm starting to roll out called Mantle. It's a vector-based map product on your own cloud, built on Lambda or Cloudflare workers. And an important part of this is that it is vendor neutral. So it works the same way on Amazon or on Cloudflare and hopefully other vendors in the future. So a bit more about PM tiles. The idea behind it is kind of like cloud optimized MB tiles, where MB tiles are a SQLite container of ZXY tiles. These are agnostic to the actual tile content. They can be vector, they can be raster, they can be scientific data. It has an open source spec on GitHub. It has implementations right now for Python, for Go, as well as direct to the browser from storage. With Leaflet, I have a plugin for Map Libre, and I'm working on CPCanoe output. And this is similar to other projects at this, there's other talks at this conference, like Kotar, ComTiles, Tilebase. Same idea, which is a range-based indexed sort of archive container for tiles. So PM Tiles is built on cloud native principles, HTTP 206, spatial indexing, and most importantly, commodity cloud storage. So what about cloud storage? I'm going to tell you what I learned from real world deployment of vector PM tiles on different clouds, not just S3. It also applies to other formats like FlatGeobuf, like COGS, like Copix. The challenge areas I'm going to briefly go over are around performance, security, and freshness. Performance, there's this quote, which is, don't underestimate the bandwidth of a station wagon full of tapes or shapefiles going down the highway. So that's one definition of performance, which is bandwidth. That concept of performance is usually not what we're talking about with cloud optimized. Optimized means low latency, not high bandwidth. Low latency enables Slippy maps, it enables interactive queries, it enables grabbing a piece of the data from the full data set. And one really important part of latency is HTTP version 2. Now that enables multiplexing where you can have many of these requests in parallel. But most vendors actually don't support HTTP version 2 on their base storage product. They usually reserve that as part of their CDN. Of the big ones, I think Google Cloud is the only one that has HTTP version 2 as a default. byte serving plus compression. For vector formats, they don't have a domain-specific compression built in like PNGs or JPEGs. And partial content is incompatible with the default content encoding sort of gzipping of the web. Browsers don't support a general purpose decompression API yet. And multi-part ranges generally are not supported on cloud storage. Security. Serving files direct from storage to the browser is good. That's a really compelling use case, but that's cross-origin usually. And of the major cloud providers, not all of them allow multiple origins to be defined for cores. S3 allows it. Other storage providers only allow one origin or just the wildcard. And if you have the wildcard, there's this problem which I call the Napster or Mapster challenge, which is that if you have range requests to download a part of the file, well, your users can just download the whole file. It's almost like Napster for maps. You can just download these data sets with no DRM, and that risks these runaway costs. If you're paying per gigabyte of egress, then anyone can just download the entire data set. It might cost $1 per user, but that adds up pretty quickly. There's no way to limit on these storage providers, only 206 range requests. And I think requester pays is a good solution, but right now that's very vendor specific. Freshness. Even though cloud optimized formats are read optimized, the world is changing. The data does update. The convention is to just replace the whole file on cloud storage. And storage providers, they all implement e-tags. There is one e-tag string corresponding to each version of the file. And implementations and caches should use these e-tags to find out when a file is stale, to know that there's new data available. So specs can take advantage of this. Conclusions, performance, security, freshness should influence the spec and implementation of cloud optimized geodata. Cloud storage is widely varying in capabilities. It's competitive, it's evolving, and don't build for S3 only. Try to make your system work on other cloud providers. That's all I have. Happy to talk about this on Gitter. You can find me on Twitter, GitHub, or email. Thanks.
All right, thank you, Brandon. And Brandon would be around here on the Gitter for the chat and questions. So we have another speaker with us, Mathias Mahar, and they're from WWE Münster, and they would be talking about OpenEO. Hey, Mathias.
Hey, yeah, that came a bit quicker than expected, but anyway.
Yeah.
Which screen is shared now? Again, it doesn't show it.
I can see your screen.
Oh, that's good. And also the slides?
Yeah, but they're not in the presenter mode now. But they're
there.
Yeah.
Okay, great.
Yeah.
So I will talk about OpenEO, which is basically cloud-native geoprocessing. So not about a file format here, but about an API and process descriptions, basically. I'm working for the University of Münster and with another couple of companies in the European Union. We're developing this since 2017. So why did we do OpenEO? Well, basically you have a number of programming languages and clients like R and Python that all want to do EO processing. And there are a number of cloud providers that do that, like Google Earth Engine and Sentinel Hub and others. But they all have their own API. So what we have right now is this mixture of things, and that doesn't really work out for people because they need to learn a lot. So we defined, or our vision was to have an API that sits in between and translates all the requests and focus on what the user needs and what he wants to achieve, and not how to do it, right? Not to learn a specific API for each of the providers, wherever the data set is that he needs. And of course, I'm working for a university, so it's always good to have reproducible results so that you can check whether what you get out from your cloud environment is actually what is the right result, and it should also be, in this case, interoperable, of course. So what is it? Well, it is a language basically for geospatial processing, so an API and a set of processes that you can run, basically, an extensible set of processes. It is cloud-based, it is open source and community-driven. So anyone can contribute to that, can propose extensions, can propose new processes, and it's all centered around data cubes, so that the data access is really easy, and you don't need to fiddle around with like files or any specifics here. What is it not? Well, it's not specifically another cloud provider. I mean, there are implementations out there, of course, for example, Open Your Platform, but it's not like a single one, right? Everyone can implement this API and processes on their existing stack of tools that they have. It's also not another geoprocessing software, of course, and it's not using the traditional GS style where you have files and tiles and where you need to figure out how to combine them. It also handles time natively. So the API is covering a couple of things like discovery for the EEO data for the processes. It also covers authentication via OpenID Connect. You can, with the predefined processes that we have, also define new, more complex user-defined processes and store them and reuse them again in another user-defined process. You can upload and download your files, of course. You can process the data that you've selected either synchronously or as larger batch jobs. And you can do on-demand processing via web service. So if you have a web map and a workflow that you want to run, you can do that on demand so that you can see or the data is just computed on the fly, basically. We have a set of predefined processes, I think roughly 150 at the moment, mostly centered around EO processing, but it's extensible. So it is basically possible to also go to other domains here and extend it. You can define user-defined processes based on the predefined processes and other user-defined processes. And then there is a concept of user-defined functions right now implemented in Python and R. That means you can upload custom code that you have previously written in Python and R and make it part of your processing chain. We have clients implemented in JavaScript and TypeScript, which power the web editor as well. So we have a browser-based client. We have Python and R as very common programming languages in the EO world. Both integrate into Jupyter as well, so you can see nice UI widgets coming out of them if you run the clients, and also works well with RStudio and R Markdown. We have a Vue.js client, but that's unmaintained right now, but we'll pick that up again in the future. So this is basically then an accept of the code that you could run. So it's really just you do all the processing on the write all the code on the client side in a language that you know, similar to how you have done it before. It's really well integrated here in Python, for example, and then it's just translated into a process that is transmitted to the backend and can be run there. The same looks very similar in R, so it's very, very easy to get used to that, I think. And if you don't want to program, you can also use the web tool, the web editor here, which is a nice UI component which covers everything, including map, showing things on the map, etc. There are a couple of backend implementations which are all open source, which you can reuse and set up. For example, for GeoPySpark, GeoTrellis, We have multiple instances running on Open Data Cube, which proxy that interface, or GraphJS, Rasterman, WCPS is also interfaced. And we have prototype implementations also for Google Earth Engine. So you can basically run anything on the Google Earth Engine as well, using our processing environment. And Sentinel Hub is also in the making. One thing that I'm working on and is basically a successor or thing that we worked after OpenEO was funded, is OpenEO Platform, a federation of multiple of these backend implementations. So you can also go to that, and it proxies a number of implementations out there. So you can have everything in one place. Yeah, that's it for me. Thank you for listening. I'm in the chat for questions. I can't hear you, Sanket.
Yeah. Thanks, Matthias, for delivering a talk. Hello. Hello. Am I audible? Hello.
Oh, yes.
Yeah.
Is it okay?
Hi, Sylvain. Can you hear me?
Hi, thank you.
We hear you.
So I am Sylvain Brunetto from CS Group. At CS Group, we work on geospatial data, and I am very happy to talk about EUDAG in this fantastic conference. Sorry. Yes, EUDAG is for Earth Observation Data Access Gateway. Came from the observation that there are lots of different Earth observation data providers like USGS or the Copernicus GIAS and many more. And for each of them, provides different APIs. For data discovery, we can have, for instance, more or less customized OpenSearch, CSW, or Stack that is more and more adopted as the new standard for search APIs. We have different interfaces for authentication using a token, OAuth, or OpenID. And for data access, we can also have HTTP download, object storage, or direct file access. EUDAG provides a unified API for search, authenticate, data access, and also to metadata using OGC OpenSearch for Earth observation extension as reference. For search purpose, EUDAG can be seen as a client for Stack API, Static Stack, and many more other protocols. EUDAG has a Python API and command line interface that are as simple as possible, like EUDAG search and EUDAG download. You can filter your searches using standard spatial or temporal parameters with many formats supported for geometry, like well-known text, bounding box, shapely geometry, or even a location name from a shapefile entry, like a country. You can also use any other criteria supported by the providers, like cloud cover percentage, orbit number, online or offline data, file ID, etc. You can also list all providers or only the ones for a given product type, list all the product types or only the ones for a given provider. You can apply crunches to your search results, which are advanced local filtering, and also order and download offline data and do many more advanced stuff. Using the command line interface, you can run nearly the same commands as in Python and also run EODAG in server mode. For providers that do not have a stack interface, this feature can be very useful. EODAG will act as a stack API proxy to the non-stack provider, and the user will transparently benefit from all the stack ecosystem, like the stack browser for his non-stack provider data. Collections will be mapped to available product types, and the catalog tree will be generated using dates, countries, or cloud cover percentage ranges. EODAG is built around plugins and keeps being extended to handle new APIs and have new capabilities. You can install EODAG Cube for having direct access to product data through Xarray. And if you search on a stack provider, you can get data from an item asset pointing to a cog, or you can also only stream to a projected subset of your choice. This is done internally using Rio Xarray. You can also use the same method to get data from a downloaded NetCDF or JPEG 2000 inside a Sentinel Safe product. Other EODAG plugins can provide you access to specific data providers, like EODAG Sentinel Sat for Copernicus Access Hub. EODAG has also a JupyterLab extension, providing you a simple and useful user interface. Located in the notebook side panel, it will help you search for data, withdrawing your area of interest, selecting dates, product types, cloud cover, or other criteria of your choice. Search results are then graphically displayed with quick looks and metadata. For downloading using EODAG, the extension will automatically generate a code snippet and insert it in the notebook. EODAG is open source, so feel free to use it or contribute on GitHub. You can post there your bugs or feature requests. You will also find on Read the Docs a well-furnished online documentation with lots of examples and detailed notebooks. Thank you.
Yeah, thank you, Sylvain. So before we start the next talk, we have some time for questions. So if there are any questions for the speakers who have already delivered their talk, please post them into the chat, and we will be more than happy to take it away.